Hi everyone, I'm Kevin Williams. Welcome to our first episode of Beyond the Beam. Beyond the Beam is a series that we put together in conjunction with Severum 360. It's an initial lecture, it's an initial series of 20 lectures, all aimed at lasers, IPL, the science, applications. We're going to be looking at maybe some innovative protocols, new way to combine devices, all based around the aesthetic industry. Episode one, we've split into two parts. This is going to give us a great introduction. So, episode one, the first part is cracking the code of laser physics, what every practitioner needs to know. Part one. A little bit about myself. I've been in the industry now for over 40 years. I've been involved in research and inventing numerous laser technologies and applications. My background is electronics and laser engineering. I was fortunate enough to work with the original team that invented the first ruby laser for hair removal. I wear a couple of different hats. I'm the Chief Technical Officer of Wynyard Aesthetics Academy. I lecture on the facial aesthetics program in conjunction with Greater Manchester University. And I'm the Technical Director of an online company which is named after me, Kevin Williams, Laser Expert. I'm also the Clinical Director for Ceraderm 360. So I say episode one, we break it down into two parts. And what we're going to cover over the two parts is understanding what is a laser, different types of laser. We're going to touch on IPL as well, because I think that's an important part. We're going to look at core parameters and light tissue interaction. So we're going to, as I said, we'll split that into two parts. So a big thank you for Ceraderm 360, because without Ceraderm 360, we wouldn't have been able to put this together. There's lots of future episodes planned. Some of the exciting when we got coming up in episode two is sub-ablative lasers. We're going to be looking at combination therapy. We're going to look at the parameters of CO2 laser. We've been asked to talk about this. We'll look at it, how you introduce technology into your clinic, what to look for when you purchase a hair removal device. And then something I'm really passionate about, I want to spend some time talking about vascular lasers and importantly, the science behind them. Use all the links to be able to contact both myself and Sarah. Okay. We're going to jump straight into it. And I guess the important question, what is a laser? It's an acronym. Laser stands for light amplification by stimulated emission of radiation. What does that mean? Certain materials, we can put energy into them to stimulate a release of a unique wavelength of light. So laser is basically a way of converting one type of energy into another. So we use electrical energy to convert into light energy. Certain materials can be stimulated to emit this unique wavelength of light. We use mirrors to create an amplification because we need to amplify this light to be able to get it to the sort of energy we want to be able to use. And this has got a unique properties that distinguish it from any other light source. So laser is a way of converting electrical energy into light energy. Different materials will release unique wavelengths of light. So you may have heard the term ruby laser. A ruby laser refers to the ruby rod that's used to release a unique wavelength of light. Ruby lasers will always produce light at 694. Or you may hear the term alexandrite laser. An alexandrite crystal will produce light at 755. If we take a step back and we look at the electromagnetic spectrum, so light is part of this electromagnetic spectrum made up of packets of energy we refer to as photons. Photons travel travel at the speed of light, and they travel in a wave-like pattern. And that wave pattern is a defined wavelength and frequency. And we're going to start off by having a look at the electromagnetic spectrum. So when we look at the electromagnetic spectrum, it's really broken into three sections. We have visible light from 400 to 700. Then we have near infrared light from 700 to 1200 nanometers. And then we have far infrared light, which goes from 1200 to 10,600 nanometers. Now, these three really break down into two groups. Your visible light from 400 to 700 and your near infrared 700 to 1200 are called colored absorbing wavelengths. So the light below between 400 and 1200 are colored absorbing wavelengths. When we go over 1200 nanometers, the absorption in water takes over. So light above 1200 is water absorbing wavelengths. Now, we're going to talk about IPL because it's an IPL flash lamp. It's often used to create as part of a laser cavity. So when we fire an IPL, and we will touch on them later, with an IPL, the way it's constructed, because with an IPL flash lamp, you're passing it through water, it ends up delivering a band of light, pure band of light from 400 to 1200 nanometers. Okay, and the importance of that will come on when we start talking about IPL. So we've got these predominantly two bands of light. We've got color absorbing and water absorbing wavelengths. Now, there are wavelengths of light below 400 in the ultraviolet spectrum. There are like cyma lasers, which are used for treating psoriasis and eczema. And these are in the ultraviolet range. And ultraviolet light, like far infrared, is also highly absorbed in water. So we've got these two distinct bands of light. Now, there's also a light here. There's also a line here at 2000 nanometers. And at 2000 nanometers, when we pass over 2000 nanometers, the absorption in water becomes so great that the lasers become ablative. So lasers below 2000 are non-ablative, and then lasers above 2000 are considered ablative. So we have non-ablative and ablative. So as the water absorption becomes so high and we cross 2000, we get these, these wavelengths become ablative lasers. So also then there's a special wavelength, and we're going to put we've put, I think it's episode 2, where we're just going to be talking about sub-ablative lasers. These are a really new technology up and coming, which is really starting to change the industry. And sub-ablative lasers are 1927 nanometers, and we're going to touch on those in a little while. Yeah. So we've predominantly got two bands, but we got this third group called sub-ablative lasers. Now, when we look at color absorbing wavelengths, the first thing we're going to learn of any use today is that color absorbing wavelengths, the longer the wavelength, the deeper the light will go. So the longer the wavelength from 400 to 1200 nanometers, the deeper the light's going to go. So you can see a 532 KTP laser is pretty superficial, but the Nd:YAG at 1064 is much deeper. So we can control the depth of penetration by the wavelength when we're looking at color absorbing wavelengths. Now, when we're looking at water absorbing wavelengths, there are some differences. And I'm going to spend, if you look at a 2790 erbium YAG and you look at a 2940 erbium YAG and the CO2 laser, there are some differences in depths of penetration. Okay. I'm going to do a whole lecture on CO2 lasers because CO2 lasers have really come back into fashion because the CO2 laser, I can manipulate them to make them less sort of with very superficial penetration or deeper penetration. I can make them produce less heat or more heat. Okay, we're going to look at the differences of these later in different lectures as well. Okay, so the important thing with water absorbing wavelengths, we control the depth by the amount of energy we use. And this will be relevant to any water absorbing wavelength. Okay, so water absorbing wavelength, if I, on this particular, this was based on a 1565 nanometer non-ablative water absorbing laser. 15 millijoules is going to go to 400 microns. But 100 millijoules will go to 1100. So we control the depth of penetration with these water absorbing waves by the amount of energy we use. And that becomes important because if I want to go deep into a scar, I need to know I'm going to have a higher energy to go deeper. So we've learned two ways we can control depth of penetration. We can control it by the wavelength when we're looking at color absorbing wavelengths, and we can control it by the energy when we're looking at water absorbing. We describe this radiation, we measure it, we measure the wavelength in nanometers. A nanometer is 1 billionth of a meter. It tells us where in the spectrum the energy sits, what color the beam is, how much energy the photons are carrying, and how, more importantly, how the beam is going to interact with tissue. And in the second part of this first episode, we'll be just looking at that in detail, the interaction of the photons with tissue. So if we look at common laser wavelengths that are used, the CO2, I said I'm doing a whole, going to do a whole webinar on CO2 because it's a really up, it's trendy laser at the moment. And that's an ablative laser. Then you get the 2940, which is another bit often referred to as a cold laser because it doesn't produce heat. We look at that later on as well. Then you get a 2790, which is somewhere in between. Then you've got the thulium laser, which is this incredible technology, which is called sub-ablative, which we're going to touch on today, but we're going to go into depth in episode 2. And then you've got the 1726 nanometer diode laser. You've got various erbium lasers. An erbium crystal can be chemically altered quite easily. So you've got 1565, 1540, 1540, 1520. There's lots of these wavelengths around there, all working pretty similar. Then you've got one of the most useful lasers that I think every clinic should have in the neodymium YAG at 1064. You've got various hair removal diodes then at 805, 808, and 810. You've again got the Alexandrite laser, which is a hair removal system at 755. Then you've got various dye lasers at 585 and 595. And then you've got the KTP laser at 532. Okay. So what have we learned so far? We've learned that visible light, the light that we can see, is from 400 to 700. We've learned that near infrared light is from 700 to 1200 nanometers. We've learned that far infrared light is 1200 to 10,600 nanometer. We've learned that an IPL delivers light from 400 to 1200. So an IPL um, combines both the visible and near infrared light. We've more importantly learned that with color absorbing wavelengths, we control the depth of penetration by the wavelength. And then what we also learned then is that when we go above 1200 nanometers into the water absorbing wavelengths, we control the depth of penetration by the energy. We can also learn how spot size is an impact as well, and that's later on. So wavelengths below 2000 are non-ablative, and wavelengths above 2000 are ablative. Okay. We're going to start off by understanding what an IPL is. So an IPL stands for intense pulse light. It's a flash lamp um, producing a broad spectrum of light. And often people say to me, what's best, Kevin? Is a laser or IPL best? It depends on the application. What we can say is an IPL are less selective than a single wavelength laser. But an IPL can produce multiple wavelengths, so it can target multiple chromophores. So due to the versatility, an IPL you can use for, you can change filters to treat different types of condition. And we take 2000 volts and we put this across a flash lamp. That emits this burst of white light. And then we use some sort of waveguide to guide the light down. So this is, you can see here, these are filters that you put in. And in these handpieces, you can see one here, you've got this waveguide. And the idea behind a waveguide is try and give it some sort of coherence, okay? To try and get it to be targeted. Some people use quartz. Some of the early systems use quartz. They used to tend to chip and they get degraded quite quickly. Modern systems use sapphire. Sapphire is preferable because it's much more efficient. It's very durable, provides more energy to tissue, and it's got incredible cooling properties as well. So the light coming out is incoherent light. That means it's disorganized and random. You've got many wavelengths of multiple colors of light, and it's a very divergent beam. So when you get a divergent beam, all going in different directions, hitting a tissue, you get a huge amount of reflection of light. So you lose a lot of the energy by reflection off the tissue. And so the divergent beam, we need to give it a path to it, get it to its right destination. So we use a waveguide. As I said, this is a waveguide. It's a solid block. As I say, most people use sapphire, and sapphire is more desirable because, as I said earlier, it enhances transmission. It's durable. You can only mark sapphire by with a diamond, and it's always cooler than room temperature. It's an interesting test if you ever want to try this. I talk about it on my full core knowledge course where you can take a screwdriver and if you put a screwdriver across the front surface of a sapphire, it won't damage. If it's quartz, it'll start to damage it. Most people won't let you try that. Okay. So with an IPL, we use different filters to let different bands of light out. So we've got a filter in to let different bands of light out. Now, some companies have interchangeable filters. So you have filters like here, you can just put different filters in, and some are fixed filters, okay? So a red filter will only let red light out. That's not true, okay? They let bands of light out below the value, and we'll have a look at this in more detail. One of the things to be aware of is make sure if you're using a interchangeable filter that the filter's not damaged. Someone sent me a photograph of burns, and it looked like, if you look at this here, this is the head, that's the tail, and this is the flat bit. This looks I don't know if anyone plays Monopoly, but it looks like the sort of dog off Monopoly on the Monopoly board. And this lady had these little burn marks all over her leg. All I said is, send me a photograph of the filter. And these burn marks lined up perfectly with this filter. Okay. So what's happened here? They must have got some oil on it. The coating's come off, and therefore then the light is not being filtered and all the wavelengths are coming through. So it's important that when you're using the outstanding advantage of interchangeable filters, it's easy to change the wavelength. Okay. But be careful and make sure you put them up to the light so you can see light shining through to make sure they're not damaged. If they damage, you should replace them. And, you know, people will say, well, how long do they last? It depends how long you care for them. It's about not getting dirt on them, not getting oil on them, and regularly cleaning them with optical cleaning solution or wipes. Okay. Um, Fixed filters means that the filter can't get damaged because it's in the handpiece. But the disadvantage is when you want to change the wavelength, you have to change the whole handpiece. Whereas if you've got interchangeable ones, you can change them easily by just changing the filter. Both have got advantages and disadvantages. I've used both systems and they both work really well. Okay. So if I select a fifth filter, a 515 filter, what's going to happen is we put the 515 filter in and it blocks the light below 515. So what it does is let a band of light out. Now in the second part of the course, we're going to go into this graph in more details. So the green light is the absorption of light in melanin. The red is the absorption of light in oxyhemoglobin. And the blue is the absorption of light in water. So if I put a 515 filter in, I block the light below 15, so I let this band of light out. Now it's not quite even, because if I look at the spectral output of a xenon flash lamp, most IPL manufacturers use xenon flash lamps, and that's got a certain gas in it, which gives you a certain profile of the output. So if you look at the spectral output of a xenon flash lamp, it actually looks something like this. So now, if I superimpose that on top of my 515 filter, what I can see here is that the bulk of the energy is delivered in this first 150 nanometers. So the bulk of the energy is delivered from about that 515 to 665. So the bulk of the energy is delivered here. Now, why would that be quite useful? It's because if I put a 515 filter in, most of my energy is going to be superficially absorbed in green. You can see by green and yellow. And what this curve is telling you here, it's got a preferential absorption in blood. Okay, so that's going to give me really good absorption in superficial capillaries. They're going to have to be superficial because this energy is not going to go deep enough to say to treat a leg vein. And we learn about that later in the second part as well. Okay, if you learn nothing from this webinar at all, then there's a cool thing you can do. Because if you have got a crystal, and one of the things that people don't do with an IPL, if I push an IPL, I don't know if you can see it on the video, if you can see me in the corner, if I push the crystal in, I can take the blood away. And if I take the blood away, I can now change it to get an absorption in pigmentation. So now you can see you get this superficial absorption and pigmentation. If you learn nothing from today, if you use one of these, if you're gonna use something like this sort of filter, put pressure on if you want to take the blood away to treat pigmentation. If you don't want to treat pigmentation, take the pressure off. And then if I want to perform hair removal, I want the light to go deeper and I want it to be preferentially absorbed by melanin. So if I choose a 6.9 filter, I can block the light below 695. So now what I can do is deliver the energy and have preferential absorbed in melanin. And again, if I put pressure on, I can reduce this absorption of blood so I can maximize absorption in melanin. Okay, so cut-off filters cut off the unwanted wavelengths below its value. So if I go back a slide, and I put an 800 filter in if there was one available, it'd block all the light below 800. Okay? So cut-off filter cuts off the unwanted wavelengths below its value. Now you can also get what are called notch filters. Some manufacturers use a dual band notch filter for vascular. So what they do, they put a filter in which takes away the superficial absorption in blood, takes out the high absorption in melanin, and then reduces two bands of light, which can be used because we know far infrared is really good for vascular as well. We can use these two bands of light for treating vascular lesions. Okay, that's just a game changer because a notch filter is going to give you a more targeted approach. Then you can have a single band. If you've got enough energy, you can have a single band. Then what you can do is deliver almost a pure band of green and yellow. That gives us very much more improved results for an IPL. If I want to use an IPL for treating superficial capillaries, I personally wouldn't necessarily jump at using an IPL for superficial capillaries unless it had notch filter technology. So how is laser light different? Well, the laser light has very specific properties. It's a single wavelength of light. It's coherent. That means all the beams are identical in time and space. It's a collimated beam. So what's the advantage over it over an IPL? Well, the outstanding advantage is you can choose a wavelength specifically to target an individual chromophore. So if I want to do something like a leg thing, I can choose the right wavelength that's going to target the particular depth and the oxyhemoglobin to get the best absorption possible. Okay. Now, because it's a collimated beam hitting the tissue, there's very little reflection of light. So also we can get more of the energy delivered to the target chromophore. So the outstanding advantage of a laser is you can choose the correct wavelength to get the correct effect on a single chromophore. That's what's exciting about lasers. And actually, people often think of laser must be much more difficult to use in an IPL, and that's not true. If someone's skilled at using an IPL, they're going to find using a laser pretty straightforward. Okay. So this is a basic laser schematic. So we've got our lasing medium. We have mirrors either side to create an amplification. So we put energy into the medium, and the medium becomes excited, and you get this photon amplification taking place. It's the medium that generates the wavelength. So if I'm using a ruby laser, a ruby crystal, it'll produce light at 694. If I'm using a KTP crystal, it's going to produce light at 532. So it's the medium that generates the wavelength. So what happens is we put the energy in, you get a photon released. The photons start bouncing back and forth. As one hits another one, it produces two, and subsequently four, eight, and they build up. There's millions of photons bouncing back and forth. Eventually, they become fully aligned, and then you get a pulse of light coming out. Now, that pulse of light can be to create a thermal effect. An example of a thermal effect, like to produce heat, would be, say, hair removal, removing veins. Photoablative is, it could be photoablative, is when you use a wavelength, a water absorbing wavelength, and you use that for stimulating collagen or cutting tissue. Or you can get a chemical effect called photostimulation, where we use low doses of light over a longer period of time to change the chemistry of something. And typically, we're going to be using microseconds to seconds. Okay. But then you can do a thing called Q switching. Q switching stands for quality switch. And it's a technique in which we can use, which a technique where we can change the laser cavity from what would have been a thermal cavity to an acoustic cavity. And we can produce lights at nanoseconds or picoseconds. Now, what that allows us to do, so typically your Q switch would fit in between the partial mirror and the laser medium. When you fire a normal laser, you go from standby to arm, and you press your foot to fire, laser fires immediately. When you're in a Q switch system, when you go from standby to armed, the laser immediately fires. And what it's doing is storing these photons in this Q switch. The moment you put your foot on the foot switch or a trigger switch, the Q switch opens, and you get a pulse of light coming out now, which is creating an acoustic effect. It could be several nanoseconds, it could be picoseconds, okay? What this is doing, as long as it's the right color to be absorbed by the target chromophore, because you still need color absorption, okay, taking place, it'll create a shock wave, which will then blow up the pit. For instance, if it's a tattoo, it'll blow up the tattoo ink into smaller fragments of ink, and the body's lymphatic system then will take that away. So the quality switch changes what would have been a thermal cavity into an acoustic cavity. And then you can get different types of lasers. So we can have gas, solid, or liquid. Okay. Gas lasers are the ones you see in a CO2 laser for laser rejuvenation or skin resurfacing. Okay. They're also used in excimer lasers. And this is now where there's a gas in the tube. We put 10,000 volts across the gas, and that excites a photon, and we get photon amplification taking place in the same way we've already talked about. Most popular systems are solid state. This is where we're using a crystal. So it could be a KTP crystal, it could be a ruby crystal, it could be a neodymium YAG crystal, it could be an alexandrite crystal, it can be an erbium YAG. And these are probably the most common ones because they're easier to control temperatures, etc., easier to run. And that basically involves using a crystal as your medium and firing white light, so 2,000 volts across your white light. White light goes into the crystal, and we get this photon amplification taking place. And then we get diode lasers, which are slightly different. And we're going to come on to diode lasers in a few slides' time. Yeah. And then you can get liquid lasers. So liquid lasers, the two popular wavelengths are yellow lasers, 585 and 595. Liquid lasers where you have a liquid dye, so it's an organic dye molecules, and they fill normally mixed with ethanol, and you have this flowing through a tube. We put our IPL flash lamp, or we could take a flash lamp, 2,000 volts flash lamp. White light goes into the yellow liquid, which creates then when we use mirrors to create amplification, and then we get this pulse of light coming out. And the light coming out of that depends on the organic dye that we use, but the typical popular ones are 585 and 595. And these are used predominantly. 595 is used for vascular lesions, 585 is for vascular, but there's a new application for treating acne with it as well. Okay. Diode lasers are different, okay? Diode lasers are different because they're optoelectronic devices which convert electrical energy into light energy, okay? And basically what you have, if this is my diode chip, you've got these optical grooves which act as a lasing cavity. Behind you, you have millions and millions of semiconductor materials. So you've got these P and N junctions on top of each other. You put a 24-volt direct current signal across it, and it becomes excited. And what that does then, it creates this effect of electrical current flow where the electron and hole, so your positive and negative, will occupy the same space. And when that happens, you get a release of a photon. Okay, so this is another way to generate a laser beam. Okay, the problem is with this type of system, they're using low energy to begin. They generally have much lower energy outputs, and uh, we're not going to cover this in detail today, but there's a calculation to work out the energy. So our joules per centimeter squared, so our energy per centimeter squared, is the output of the laser in wattage times the exposure time divided by the area. Okay. Now, if you take my word for it, that on average, depending on spot size, typically we need about 20 joules per centimeter squared. If I'm using an alexandrite laser, for hair removal. And if I'm doing fine hair, I need a pulse duration of 3 milliseconds or less. Okay, but certainly much less than 10 milliseconds. Okay, so we know that energy is wattage times pulse duration divided by area. So if I want to work out a pulse duration, if I know that would be my energy times the area divided by the wattage. So if I take the world's leading diode laser, which is a 12 by 12 and 2,100 watts, okay, then my energy I know I want is 20. My spot size is 1.44 centimeter, and the wattage is 2,100. what that will tell me is that will generate that for me to create that 20, I need a pulse duration of 13.7 milliseconds. Therein lies the problem with diode lasers. Because they're low energy devices, they can't generate enough energy in a short enough pulse duration for certain conditions. So you very rarely see this type of diode laser with the diodes built into the handpiece like this. You very rarely see these being used for vascular conditions, and most of them don't work for fine to medium hair. Some of them are good for medium to fine. I haven't come across a system yet, in my experience, that treats fine hair successfully, like you would with, say, an Alexandrite laser. So these are low energy devices. Now, someone said, well, I've got a machine which is 4,200 watts. And I've done a whole course and I've got another one coming up on diode lasers. But my 4,200 watts, if that's over a spot size, which is twice the size of 12 by 12, then it's going to work out at the same calculation. So typically, these are low energy devices, so they got some limitations. So just be aware of that. Okay. So a laser gives us a fixed wavelength determined by the laser medium. They're highly coherent and it's a collimated beam. It allows us to get the best possible transmission into the tissue for a specific target chromophore. And that's what's exciting about a laser. So that concludes uh, episode one, part one. I look forward to seeing you soon for part two, which will be available next week. Thank you for listening. And if you like the series, please subscribe. Look out for us on the different social media platforms.